Howdy. I'm going to be talking today about how to estimate areas. And to get at that, I want to consider a familiar curve to you, the curve y equals x squared. And I want to form a region by using the curve y equals x squared as a boundary, and also the vertical lines x equals 1 and x equals 3. And finally, the x-axis for the line y equals 0. And I want you to observe that these four curves together create a completely enclosed region. And what we're interested in is the area of this region. Now, if this region were a simple shape, like a triangle or a trapezoid, then we would simply employ a geometry formula. Unfortunately, it's not a simple shape because this top curve right here, y equals x squared, is not a straight line, so we don't have a trapezoid. And we don't have a circle or any other such thing. So we're going to have to estimate. And it may have already occurred to you that we could probably simply count up squares. So if I counted the squares, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 for those two, maybe 15 for those two, 16, maybe 17 for this plus all that. So about 17 squares. That's our first estimate. And each square, as you can see, has a height of 1, and it has a width of 1/2. So the area of each square is 1/2. So I get a total area here of half of 17, or 8.5. So that's one way to estimate the area. You could imagine that it takes a lot of counting to do that, and so we might want to do that a little bit faster. And we're going to do that with rectangles. The basic idea is that we're going to sum up rectangles in order to get an estimate for our area. Here's how we're going to form the rectangles. First of all, we're going to observe that part of our region goes parallel to the x-axis, and it stretches from x equals 1 to x equals 3. Our interval is 1 to 3. And so what we're going to do is to take that interval 1 to 3, and we're going to divide it up, or partition it. And what partitioning simply means is that we're going to choose some x values in here. They might be equally spaced or they might not. Here, I am going to choose the x values 1, 1.5, 2, 2.5, and 3. And those 5 x values now form 4 subintervals. The first subinterval is right here from x equals 1 to 1.5. The second subinterval is from 1.5 to 2. The third is from 2 to 2.5. And the last one is from 2.5 to 3. And what I want you to observe about these 4 subintervals is that when I take their union, when I put them all together, what I get is exactly the interval that I have right here. But when I take their intersection, when I look at the points they have in common, the only points that they have in common are 1.5, 2, and 2.5. In other words, the subintervals do not overlap except right at their boundaries. So that's what a partition is. They all together have a union of the entire interval, and they only intersect right at their boundary points. Now, we worked pretty hard to get this partition and to write it out, but actually, it's in practice, it's fairly easy to do. We start with our interval, and we decide we start with the interval, and then we decide how many subintervals we want we choose in the number of subintervals. In our case, we had 4, n equals 4. And then that allows us to compute a width for each subinterval, and it's very easy. The width of the subinterval is going to be called delta x, and its size is the total length from A to B divided by the number of subintervals, b minus a over n. And if we make this choice of partition, which is the usual method, then we call this an equally spaced partition. And I would say 8 times out of 10 mathematicians will choose equally spaced partitions. The equal spacing is not absolutely necessary. I could have chosen a subinterval from 1 to 2, and then a different one from 2 to 2.5, and then a different one from 2.5 to 3. And that would be a partition with 3 subintervals, not equally spaced. There's nothing wrong with that. But what I do require is that the union of all of my subintervals adds up to the entire interval, and that the subintervals only overlap at their boundary points. Okay, having partitioned my interval, now I'm going to create rectangles. Let's go back to our n equals 4 equally spaced scheme, and I'm going to go to my first subinterval right here, and I am going to choose a point on the curve within that subinterval. Let me choose this point right here at the top, and I'm going to use that as the height of a rectangle. I'm going to draw myself a rectangle that intersects the curve somewhere. And I'm going to do the same thing for the next subinterval. And for the next one. And for the last one. And now what I have are 4 rectangles whose area roughly estimates the area of the region. And I say roughly because you can see that all of this right here is error in my estimate. These circled areas are places where the rectangle overestimates the area of the region. So we'll have to do something about that. But for now, we're simply going to compute our area estimate. What I did to get this height was I went to a particular place on the curve. And the particular place on the curve that I went to was the height that corresponded to x equals 1.5. And the height right at that point was f of 1.5, or 1.5 squared. Likewise, for the next subinterval, I went to this point on the curve, which is where x equals 2. And the height of that rectangle was f of 2, or 2 squared, which is 4. And finally, well, not finally, for my third subinterval, I went to x equals 2.5, and the height of my corresponding rectangle was f of 2.5. And for the last rectangle, I went to x equals 3, and the height of that rectangle was f of 3. If I now add up the rectangles, well, I'm going to do each one individually. So for my first subinterval from 1 to 1.5, the height was like this. Height, subinterval, and width. Okay. So the height here was f of 1.5. The width was the width of the subinterval, which is 1.5 minus 1.5. Because I did an equally spaced subinterval, all of my widths are going to be 0.5 here. For the next one, my height is f of 2. My width is 0.5 again. For the next one, my height is 2.5. My width is 0.5. for the last one, my height is f of 3 and my width is 0.5. And now here's why we chose rectangles. Because rectangles' areas are easy. It's simply height times width. And f of 1.5 is 1.15 squared. Let's do that here. .15 squared is 2.25 times 0.5. And f of 2 is equal to 4 times 0.5. And f of 2.5 is equal to 6.25 times 0.5. And f of 3 is equal to 9 times 0.5. So that when I now add it all up, what I'm adding up is all of these values right here. And you can check for yourself that the value that you get is 10.75. So that my area is approximately equal to, and here, because I'm adding a whole bunch of like things, I'm going to express this as a sum. I'm going to sum up from the first subinterval to the last one, which is the fourth subinterval. And I chose in each subinterval an x value, and I multiplied that by my delta x. And although my delta x was the same for each of these subintervals, in general, they don't necessarily have to be. Now, the value that we got here, 10.75, seems a little bit large. When we estimated back here by counting squares, we got about 8.5. And we're not too surprised that this estimate is a little bit large because we can see visually that there is a whole lot of area of rectangles that lies above, that lies outside of our region. So we call that the error in the approximation. The difference between our estimate and the true value, whatever that may be, is the amount of error. And we'll have more to say about that in the future. Okay, so let's walk through the process that we used to get this estimate, and then we're going to come back and do a couple of more estimates. First, the procedure is to choose a partition of the subinterval, and the usual choice is to make it equally spaced in which case the width of my partition is going to be b minus a over n. Then after we chose a partition, we mark that partition on the graph, and that just keeps our head straight. And then for each subinterval, we chose an x value, and we're going to label that c sub I. It's a c somewhere in the subinterval. And the subscript sub I right here refers to the fact that we are going to number these c's from 1 to n, 1 for each subinterval. That's all the hard part. Now the easy part is just adding up the area, because the area is going to be approximately the sum from first to last, from I equals 1 to n, of f of c sub I times the width of each subinterval. Notice that the delta xi are also numbered because they might be different from each other, but usually we're simply going to use the same number delta x equals b minus a over n for each of those delta x's. So this is the basic procedure, and we have a name for this sum, when we are multiplying function values times widths, and the widths together partition our subinterval. We name this after the mathematician who first played around with them in a formal way, and that is Riemann. We call this a Riemann sum. The Riemann sum is simply the sum of function values times widths, where the widths partition the subinterval. That's the procedure. Now let's go back to our curve, back to our region. And what I'd like to do is to make a different choice for our C sub i's. So we'll sketch the region again. Here, and here, like so. And we're going to use the same partition that we did before, an equally spaced partition with 4 rectangles, 4 subintervals. And now we're going to, for each of our subintervals, we're going to make a different choice of x value. And for my first subinterval, from 1 to 1.5, I'm going to choose c equals 1. That is this guy right here on the left. And that gives me a rectangle that looks like this. And for my subinterval from 1.5 to 2, I'm going to choose c equals 1.5. And I said I was going to number these, so let me actually do that. Here's my c equals 1.5. And notice where my rectangle height is. It is at f of 1.5, where my c value was. So let me number this. That's c1, that's c2. From 2 to 2.5, I'm going to choose c equals 2. That gives me a rectangle like so. And then from 2.5 to 3, I'm going to choose c equals 2.5. And that would be c4. So that now my area estimate has the same form as the previous one. Area is approximately equal to the sum from I equals 1 to 4 of f of c sub I times delta x sub I. But what has changed are the c values that we chose here. So that my sum, when I now write it out, I'm going to pull this down into the open so we can see it better. Where's a good spot for this? We'll take it to a new page. And just so we don't lose track, I'll rewrite the intervals and the c's that we chose for those intervals. There we go. And so now we write that the area is approximately the sum from I equals 1 to 4 of f of ci delta xi. And that's going to be 1 squared times 0.5 plus 1.5 squared times 0.5 plus 2 squared times 0.5 plus 2.5 squared times 0.5. And when you actually run the numbers, what you get is, we get 6.75, which you can see is a whole lot less than our previous estimate from the squares, and it's a lot less from the previous Riemann sum that we did. So we wonder, how accurate are these Riemann sums anyway? And here, because we didn't want to do a whole lot of computations, I only chose 4 rectangles. But you can imagine that to decrease the error, use more rectangles. Computers are particularly good at this because you know, it's some effort for us to do 4 rectangles. 8 sounds like a pain in the neck, and 16 sounds like it's prohibitive, but a computer thinks nothing of doing 10,000 of these. And in fact, at a future time, I'll show you how to do these on your calculator very, very simply, so that you end up with an accurate answer, one that's good, usually good to 3 or 4 places, without too much effort. But let's recap all of this and talk a little bit more about the choices. We started with the curve, with the region, y equals x squared, bounded by x equals 1 and x equals 3 in the x-axis here. And we estimated the area of this region by partitioning the interval from 1 to 3, like so, and then choosing an x value for each subinterval, and then compute the area is approximately the sum from the first subinterval to the last of f of ci times delta xi, just like that. So this is the method in brief. The only part about it that is at all confusing then is the choice of c sub I. How do you go about doing that? And the answer is really that there are a lot of possibilities, and I'm going to share with you the most common possibilities. So I've got a subinterval c sub I, and just to be clear here, we've got an interval a to b, and the best way to number the x's for your interval is to start with 0. So this is x0, x1, x2, x3, x4, and that way the number of your last x is the same as the number of subintervals that you have, 1, 2, 3, 4, and so on. So for each subinterval, we have to choose a CI, and now I want to share with you some common choices. Far and away, the two most common choices are left sum and right sum. And when we do a left sum, then for each subinterval, we're going to choose the x value that is on the left side of each of those subintervals. If we were to make it formal, we would say that c sub I is equal to x sub I minus 1. You can see that in the previous example that we worked here we were doing a left sum. How do I know? Because each c sub I is on the left side of the subinterval that we chose, just like that. Likewise, we can do a right sum. If we do a right sum, then we're choosing c sub I equals x sub I. A right sum has us picking the x's that are on the right side of each subinterval. In the very first example that we did, the one where we ended up with 10 point something, we used a right sum to pick our c sub i's. Go back and look at that for just a second. You can see here that the c's that we chose were the ones on the right side of each subinterval, just like that. Those are the two most common choices. The third common choice that you need to be able to do is called a midpoint sum. And for the midpoint sum, we're not going to choose the right, we're not going to choose the left, we're going to choose the exact middle of each subinterval, so that c sub I is equal to the average of xi and xi minus 1, just like that. Let's make these three choices concrete, because in the real world, these are the three choices that you need to be able to do. So let's consider again our region. y equals x squared, x equals 1, x equals 3, and y equals 0, which is the x-axis. Because we've kind of milked 4 subintervals to death, let's do just 2 subintervals. Let's choose n equals 2, and let's make them equally spaced. You can practically do this in your head and see that this gives us x's of 1, 2, and 3. But to be formal about it, we would say that delta x is equal to b minus a over n, or 3 minus 1 over 2, which is exactly 1. And so now let's construct first a left sum, and then we'll come back and construct the other two. So if we want a left sum, then I am going to choose the x's that are on the left of each subinterval. And that's going to be x equals 1 and x equals 2. And therefore, my area is approximately equal to f of 1 times delta x, which is 1, plus f of 2 times delta x, which is 1 again. And that's 1 squared times 1, plus 2 squared times 1, which is equal to 5. Notice that this area estimate is pretty poor as an estimate. It doesn't, you know, we had 8.5 as a pretty good counting squares kind of an estimate. And this is definitely well below that. And the reason for that is simply that we only used 2 rectangles. If, on the other hand, I wanted to do a right sum, then I would choose the c's that are on the right. 2 and 3. So that my area would be approximately equal to f of 2 times delta x plus f of 3 times delta x, which is going to be 2 squared times 1 plus 3 squared times 1, which is equal to 13. And that is, again, way off because I only used 2 rectangles. And now if I choose the midpoint sum, then for the midpoint sum, I'm going to take the x values that are in the exact middle of each subinterval. So my midpoint sum is going to be the average of 1 and 2, and the average of 2 and 3, that's 1.5, that's 2.5, so that my area is approximately f of 1.5 times 1 plus f of 2.5 times 1, which is 2.25, plus 6.25, which is 8.5. Look at that. My midpoint sum actually is pretty darn accurate. Generally speaking, for a given n, the midpoint sum is more accurate than either the left or the right. But it's a little bit more of a pain in the neck because you have to go through and compute your CIs. So there's a trade-off. How much work do you want to do versus the accuracy that you want to obtain? Well, let's summarize all this. The summary is this, that the area is approximately a Riemann sum. That's it. But now, having said all of that, the way in which we go about computing this Riemann sum is, first of all, to partition, then to choose the C sub i's, and then to construct the Riemann sum. And although it looks like a lot of work, I've done a lot of writing and work here as a preliminary way of explaining it. When we actually get into it and do it, it's not so bad. So to illustrate all that, I'm going to close with one final example. Here I have the curve y equals cosine x. And I want to form the region from x equals 0 to, well, I don't want to shade that too much here. Let's erase that a little bit. I want to form the region from x equals 0 all the way out to x equals pi. And that is going to be all of this together with all of this. So let's define this region properly here. We're going to have the curve y equals cosine x. We're going to have the vertical line x equals 0. We're going to have the vertical line x equals pi. And we're going to have the line y equals 0, which is the x-axis. For a long, long time, all of our regions are going to have the x-axis as a boundary. That will eventually change, but really for this chapter, we're going to have the x-axis as the boundary. And now what I'd like to do is I would like to compute some areas here. I want you to notice that some of my region lies in the negative part. It lies in the y is less than 0 range. And because of that, when I do function times width, I'm actually going to get a negative number. So that when I compute the area of the entire region, what I'm not going to get is a geometrical area, but instead I'm going to get a net signed area in which all of the part of the curve that is above the axis here is going to get a positive area, whereas all of this here is going to count as negative area, just like that. And I suspect already that when I compute the net signed area, it looks to me like the positive part and the negative part have equal but opposite areas. So I suspect that my net signed area should be 0 when I add it up. And let's see if that actually happens. So, let's see what we get. We're going to compute net signed area. And so we begin by partitioning. And we want to choose a reasonable sized n. The larger the value of n that we choose, the more accurate our answer will be, but the more work we have to do. So I often choose numbers like 4 or 6, 5, whatever. Let's choose n equals 4. And if we make it equally spaced, then we compute delta x for our partition is going to be b minus a over n, which in this case is pi minus 0 over 4, or pi over 4. The width of each subinterval will be pi over 4, which is pretty convenient because here it is. Just like that. So we have now partitioned our subinterval. Now we have to choose C sub i's. And we can choose from left sum or right sum or midpoint sum, or we could even make other choices. I'll talk about those other choices a little bit after this final example. Left sum or right point or midpoint sum. Let's just do a left sum for convenience. So if we do a left sum, you can go back to the graph. A lot of times I'll just identify my x's on the graph. I'm going to choose the left side of each subinterval, 1, 2, 3, 4. Just like that. So that my area is now approximately the sum from I equals 1 to 4 of f of c sub I times delta x sub I, which is going to be equal to our first x is 0, and the delta x is the same for all of them. It's pi over 4. That was our first x. Our second x is pi over 4. Our third x is pi over 2. And our last x is 3 pi over 4. And now we go to the unit circle to get all these values. This is going to give me 1 times pi over 4, which is pi over 4. The cosine of pi over 4 is 1 over root 2. The cosine of pi over 2 is 0. And the cosine of 3 pi over 4 is negative 1 over root 2. And when I add these all up, you can see that these two here are going to cancel, so that I end up with pi over 4 as my area estimate. Now that's not 0, but it is around 0.75. So we figure that probably the error that we have is because our n is so small. What would have changed if I had chosen a right sum instead? Well, in that case, my partition is exactly the same. The x values that form my partition are exactly the same, but the c sub i's that I choose are different. Instead of choosing the x's on the left, I'll now choose the x's that are on the right, here, here, and here. And therefore, for the right sum, I would say that my area, which is the sum from I equals 1 to 4 of f of c sub I times delta x sub I. I don't get tired of writing that form because it reminds me of what I'm looking for. In this case, I'm going to have cosine of pi over 4 times pi over 4 plus cosine of pi over 2 plus pi over 4 plus cosine of 3 pi over 4 plus pi over 4 plus cosine of pi times pi over 4. And again, we get these values just like we did for the last sum. The only term that is different is this very last term here. Cosine of pi is -1. So that now when I add all of these guys up, those two terms cancel, and I get that my area is approximately negative pi over 4. Well, that's very interesting. For the left sum, I got positive pi over 4 as an estimate. For the right sum, I got negative pi over 4 as an estimate, and you can probably figure out what would be the most accurate estimate that I could get with n equals 4. The most accurate estimate is going to be the average of left and right, which in this case gives us exactly 0, which is in fact the exact answer. This idea of averaging left and right is going to appear again when we talk about trapezoidal sums. Well, I hope these examples give you an idea of how we do area estimates. Now, the last thing we're going to talk about are some other possible choices besides left, right, and midpoint. Left, right, and midpoint sums are the ones that are used for practical purposes. But there are a couple of sums that are very, very useful for theoretical purposes. And those are the upper sum and the lower sum. And for the upper sum, what I do is to choose deliberately the maximum value of f on each subinterval. And what I do for the lower sum is I choose the minimum possible value of f on each subinterval. And the reason that I might want to do that is that I am guaranteed that my upper sum has to be larger than the actual area. Because whatever rectangle I draw, it's going to go outside the curve. And I'm also guaranteed that the lower sum is less than the actual area. So the upper and lower sums are very useful because they put boundaries on the area. My area is no worse than the upper and lower sums. The only drawback with this is that it is very often difficult to identify the maximum and minimum values of a function, as you know from your work doing optimization. So we don't often compute the upper and lower sums unless it's particularly convenient. In the case of the region that we started with, y equals x squared, you can see that the right-hand sum just happens to be the upper sum because my curve is increasing, because f prime is greater than 0. And likewise, my left-hand sum, which is here, just happens to be the lower sum because my curve is increasing. But unless you are so lucky as to have a purely increasing curve or a purely decreasing curve, then you won't be able to use left and right for upper and lower, or lower and upper. So those are the other two choices that can be made, and these are more theoretical than practical. The last choice is interesting, and I only point it out for those of you that are taking statistics. If a statistician is trying to do an area, then what he will actually do is do a random sample for his C sub i's. For each we call this a Monte Carlo sample, so that